Thank you again. It's great to be here, and I want to welcome those of you who were here last night, and yay! And those who weren't here last night, boo! No, this is a wonderful weekend for us at the Origins Project, and tonight is going to be a great night, and I'm very excited about it. I want to repeat one thing I did say last night for those who weren't here. For me, and for all of us, it is a true privilege to be located in a place, this place, where we can fill up 3,000-seat auditorium for science. It says great things. It's true. It says great things for all of you, and we really appreciate it. But tonight is an amazing evening because, without hyperbole, it is true that I don't think there has ever been on one stage an assembly of science storytellers and communicators like this. It's very intimidating, in fact. I have had the good fortune, I realized, to appear on stage with each one of these people individually, but all together. It's going to be an amazing night. And the way it's going to work, when you got great jazz musicians, you allow them to jam. And so the way we're going to do it is we're going to bring everyone out in a minute or two, and everyone's going to tell a little science story for you, to give you a sense of what excites them about science or to how they interpret science. And each one of the people will do that, and that should take a while. And then we'll take a break. Then we'll come back, and we're going to have a discussion. Then we're going to open it up to all of you. I believe you have question cards. If you want to. Write down your question by the intermission, bring them down, and then we'll choose some questions. And after we have our discussion, we'll try and answer your questions. So that's the way it's going to go. So I want to introduce each of the panelists in order. The first person that I want to introduce is the director of a remarkable festival, which is, I would say, next to the Origins Project, the most amazing science festival in the country, the World Science Festival in New York City, and I've been privileged to be part of it 4 or 5 times. And Tracy Day is the CEO of that, a former broadcast journalist, and puts together this remarkable program of 30 to 40 different science events throughout New York, and with lots of different scientists and musicians, and it's an amazing event, and it's been a privilege for me to be a part of it. So I want to bring out Tracy Day first. Thanks, Tracy. Thank you. Next, I want to bring out an old friend of mine and one of the most well-known physicists in the country. He burst like a supernova on the stage of the public stage with his first book, The Elegant Universe. And I think of him as a long-lost son, really. And Brian and I have been together in many venues, and he is really one of the most remarkable and vibrant communicators of physics, particularly particle physics, in the country. And it's really a pleasure to welcome him back to the stage today. Brian? Papa! Okay, enough. That love, I feel it. Thanks, Brian. I'm not turning my back to you, I think. But the next person I want to bring on stage is another old friend, and I've been privileged to be on his program a number of times. And he is really one of the most amazing, well, he has the most amazing radio program in the country about science. But if you've been on the program and you've experienced it, you can see what an amazing job he does in interviewing people. Brian and I and Ian McEwen were on earlier this week, and when you're on there, you see the incredible talent. And I know that when I try and moderate these panels, what I think is I'm trying to channel Ira Flatow. And so I'm happy to bring out Ira Flatow. Thank you. Yeah, it's okay. Next, I want to bring out a little guy who is now everywhere. He's on TV. He's about to make a new series, a remake of the Cosmos series. And he's the director of the Hayden Planetarium, and in fact, I was privileged enough to be there last week for an event that he moderated, and now I'm going to return that favor to him and not let him talk either. He's a little shy, but I think we can encourage him to come out. Neil deGrasse Tyson. No, you're over there. Oh, hold on. No, you're not over there. You're over there. Sorry. Yeah. It's okay. Next, we have, as I said last night, in my own mind, the person we all look up to as one of the greatest writers about science in the history of science, and someone who changed the way science writing is done and communication is done with his book, A Selfish Gene, which was published almost 40 years ago. And it's a surprise guest because he wasn't in the original program, but he was here last night, and we'd be remiss if we didn't include in this program Richard Dawkins. That's great. Now, the next guy is a real guy. In fact, he's a science guy. And I don't think I have to say anything else. Bill Nye has been an amazing educator on television. I love watching him in Disney World each time I go to Epcot Center. And he's been a pleasure to interact with. He's also the executive director of the Planetary Society, which is a position that Carl Sagan first had. And it is truly a pleasure and a privilege to welcome to the stage Bill Nye. Thank you. Thank you. You take care of that. An amazing group. And the last person I want to welcome to the stage is a little bit different, but in fact, he communicates science in a different way. In my mind, personally, I think he is the best science fiction writer writing today. He is incredibly prolific. I don't know how he produces what he produces. And I've been with him in a number of events, and he has an incredible following. He weaves science in his stories in a way that very few science fiction writers really do effectively. And it's truly, again, a privilege to welcome Neal Stephenson to the stage. Thank you. Okay, so we're going to begin. If we go to the first slide, actually. And as all of my colleagues will point out to you, it's always about me. And so the story, I want to tell you a little science story, and it's a story about me. In a way, it's a story about what got me interested in science, because I thought that would be appropriate. This person here is Richard Feynman. This young person here is me. And Richard Feynman made me want to be a scientist for a number of reasons. When I was a high school student, I took a special summer program, and I was bored. And the teacher came down and said, "You look bored," and he gave me a book. And in fact, I think if this works, it does. This was the book. It's called The Character of Physical Law by Richard Feynman. And he said, look, this is a book by a guy who won the Nobel Prize recently for proving that antiparticles are particles going backwards in time. Wow, this is amazing. So I took the book home, and I read the chapter. I didn't understand any of it. But it was really neat. But the thing that was important for me, and I hope one of the things I like to tell students, because we tend to teach science, as I said the other night, as if it's done by dead white men. And when I looked at this, I realized, not all the problems are solved. There's still an incredible number of things we need to understand about the universe. And it was the first time that I thought a career in physics might actually be worthwhile. There were things left to discover, that all the great things hadn't been known. And it changed my life completely. Now, like all good physics undergraduates, I'm sure Brian and Neil at very least, I carried around with me the Feynman lectures on physics. He rewrote all of introductory physics in his own style. He was incredibly charismatic and an amazing teacher. And I carried them around. Again, I couldn't understand them. But I thought by osmosis, if I carried them around long enough. It was only when I was a graduate student that I really began to appreciate the depth of those descriptions. And that kind of, as I thought of being an educator, the idea, what was amazing about Feynman was that he conveyed his excitement and his interest and the integrity of science, as I'll talk about in a second. Now, I was lucky enough, as it turned out, when I was an undergraduate, to meet Feynman at a meeting up in Canada. And this was actually taken for a physics magazine. And I'm pleased we were actually talking physics at that instant. But I spent most of the weekend with him because I brought my girlfriend at the time, and she was one of the few women. And Feynman, if you knew anything about Feynman, he decided to spend most of his time with us. And besides actually teaching me how to dance, he convinced me we had long talks about adventure and seeking out adventure. And I know for him, science was an adventure, and it is for me, but it was everything in life was an adventure. Learning, just the pleasure of finding things out, as he wrote. And that became infectious for me and changed and invigorated me to become a scientist. Now, it turned out many years later, when I was at Harvard, I gave a colloquium at Caltech, where Feynman was teaching. And it was very intimidating, of course, but he asked a good question. Then he came up afterwards to talk to me. And I really wanted to remind him. I was certain he wouldn't remember our weekend together. And he wanted to ask me a question, but there was a very annoying assistant professor who would not stop asking me questions. I'm very happy to say he didn't get tenure. But Feynman walked off, and I thought, well, I'll catch him later. But he died shortly afterwards, so I never was able to tell him what he meant to me. And as a result, I wrote a whole book about Richard Feynman because, for me, he captured the way science is done. I'm going to let him tell you in the last minute his own story, or at least the way he saw science. But I want to tell you one of the facts about science, the kind of things that would amaze him and amaze me. All of you take a breath. Hold it in. I can't see. Are you still holding? No, you can let it out now. Okay, good. Well, there's a possibility, in fact, a likely possibility, that with every breath you take, you are breathing in atoms that Richard Feynman breathed out when he gave the interview I'm about to show you. And every time I'm sitting at my desk, not getting anything done, feeling ignorant and incompetent, I like to think that I'm breathing in atoms from Richard Feynman. And that sense of joy and mystery, to me, is what science is all about. And no one conveyed it better than Feynman, and so I'll let him finish this off in his own words.
You see, one thing is I can live with doubt and uncertainty and not knowing. I think it's much more interesting to live not knowing than to have answers which might be wrong. I have approximate answers and possible beliefs and different degrees of certainty about different things, but I'm not absolutely sure of anything, and then many things I don't know anything about, such as whether it means anything to ask why we're here, and what the question might mean. I might think about it a little bit. If I can't figure it out, then I go to something else. But I don't have to know an answer. I don't feel frightened by not knowing things, by being lost in the mysterious universe without having any purpose, which is the way it really is as far as I can tell, possibly. It doesn't frighten me.
He wasn't frightened, and he loved mysteries, and that's what science is all about, to me. Thanks. Thank you. Tracy, you want to go up next?
I would love to. Am I supposed to stand?
Yeah, you can go stand. You can do whatever you want.
One thing is probably obvious, which is I'm quite different from others on the stage. Actually, I'm quite different another way. I'm neither a scientist nor a science journalist. And honestly, if my former friends and colleagues, my friends and colleagues saw me on this stage with this group of people, they would laugh, because I was actually a broadcast journalist, and I covered wars, I covered politics, I covered many things, but I never covered science. And that is because we all assumed that science was boring, and that scientists were boring. And so my story is really about how I discovered that science is a great story. And I did a program in about 1999 called The Century with Peter Jennings, and I was producing a part of it called The Thinkers. And I interviewed many impressive, incredible people. And what I found that the scientists were actually more interesting and more compelling than anyone else I talked to. Actually, there were people, Richard Dawkins, Brian Greene, many others were in that program. And so I realized again that the science stories are really, they were untapped. They were, people didn't realize in the mainstream media that these are great adventure stories and many other things. So in 2005 or so, Brian Greene and I co-founded a thing called the World Science Festival, and what we wanted to do was bring science to a general audience in a very new way. We wanted to use all of the storytelling multimedia techniques you could throw at these great stories. And the key thing is we wanted to put the scientists on the stage. They were great communicators, and they often didn't get the chance to do that. So Lawrence is a wonderful participant in the festival. He has been there a number of years. And so he asked me to, as part of this talk, bring a video that would actually show what the World Science Festival is and does. So if we can bring the lights down, we can show a bit of that.
Some of the biggest names in science and the arts have gathered here in New York City for the World Science Festival.
The festival, which has been called a new cultural institution by the New York Times, takes science out of the laboratory and into the streets.
World Science Festival kicks off with a star-studded gala performance hosted by Oscar-winning actor Alan Alda.
Tonight we fly across the cosmos at the speed of art. Scientists and artists come together and give us a view of nature that is both fascinating and fun.
It is my distinct pleasure to dedicate Icarus at the Edge of Time to tonight's honoree. More than any other member of our species, Professor Hawking has traveled closest to the edge of time.
I am very honored by this wonderful evening.
What's such a great adventure about science?
The idea that we can all understand science and not have to be scientists is just a wonderful miracle of this festival.
There's a tremendous appetite in the public for knowing what science is actually accomplishing.
Is life a one-off chance?
Are our genes our destiny?
Is there a mathematical order to nature?
What the hell is mathematics?
Is there aliens in space?
This is what science is about. The excitement, the wonder, the adventure, the discovery.
If you ask me what do I hope to find, I don't know, more cool stuff.
To moderate this panel on quantum physics, do you know anything about it?
Well, you know...
The most intimidating audience to teach a short Black Holes 101 course in front of Professor Stephen Hawking.
Give us a thumbnail sketch of the beginning of the cosmos as we now know it.
You can actually do a calculation to find out how many bits are necessary to simulate the universe.
The program here tonight will discuss more dimensions than meet the eye.
Now, string theory, it's multi-dimensional, vibrating strings that are so small that there's no way to ever measure at any imaginable point in the future. And yet, people still take you seriously.
kinds of things that will be said here on this stage this evening are the kinds of things over which wars have been started.
There's no animal in the animal kingdom that has wreaked the kind of havoc that we have.
Unless we take care of the ocean, nothing else really matters.
You deserve to be punished for doing the wrong thing.
Tonight we're going to explore science and religion. Why do you still have faith in God?
What do you mean still?
You can't predict what's coming next. You can't prove what's coming next. I'll tell you what. You don't care because you're a physicist. If you can't solve a problem, convince yourself that it's not important. Forget about it.
We got to get especially young people interested in science, because by the time they hit school, it is literally crushed out of them.
I think young people care a lot more about science than we did when we were their age.
Who among the young people here would like to go to Mars?
What can people expect from a free street fair?
You won't find falafel or tube socks. This is really wall-to-wall science.
I love the idea that they're taking the exhibits out to the people.
I live for being around great young scientists because the world has amazing possibilities.
I am a mathemagician. That's 300 times 238 plus 31 squared, 71,400 plus 961 is 72,361. Let's hear it for algebra!
Is something beautiful to you because we're hardwired to like beautiful things, or because it relates to reality?
Put your stereo glasses on.
These images, they are artworks of the universe.
The storytelling has to be direct enough to move us from one panel to another panel to another panel.
Science Festival. I'll be there.
So as you can tell from that highlights reel, what we try to do is open up new avenues of entry into science through the arts, through debate, discussion, through Nobel laureates talking to children, and what we hope to accomplish. And based on the people who attend, I mean, it's been 5 years, and nearly 1 million people have attended the live events. And the goal, and what we hope will continue, is to move science out of the siloed existence that it tended to be for a general audience and smack into the middle of popular culture where it belongs. So, thank you.
Thank you, Tracy. Okay, let me call upon your trailing spouse.
That's right.
Brian.
Thank you. Thank you. So, as I suspect most of you know, you are a very unusual audience, an unusual group that would come out in this enthusiastic way in support of science. I mean, most of the world doesn't see science in that way. Most of the world doesn't see science as a story, right? Most of the world sees science as this collection of facts that they were forced to learn at some point in school and then spit it back on an exam, and they were all too happy to leave it behind after the exam was over. But of course, what could be more human than science, right? Science is about asking questions and observing, exploring the world to try to find the answers. And that's what we do, right? That's what we do since we are even little kids, right? There's so many stories that get that across, but let me just give you one to get things going. So, you know, my son, he's somewhere out here. He's 8 years old, somewhere out there. There he is, right there, yeah, good. Thank you. So when he was about 4.5 years old, I was telling him a lot of bedtime stories, and I was really trying to put some science into the stories, right? You know, so I'd have all these spaceships flying through the universe, but I was always very diligent in saying they weren't going faster than the speed of light. One night, my son turns back to me and says, "Dad, speed of light, what about the speed of dark?" And it's like a thought I hadn't really had before. But you see a young mind grappling with these kinds of ideas takes it to an unusual place. And just to be an equal opportunity parent, my daughter's also out there. And yeah, thank you, Sophia. Good, good, good. And, you know, I have, for the last few years, been thinking about ideas that are unfamiliar to most people, the possibility of other universes, the multiverse. I mean, you know, most of us were raised to think universe means everything to begin with, so how could there be other universes? And I say most of us with some forethought because, you know, my kids have heard me talk about this stuff all the time since they were really young. And Sophia, when she was 3.5, I was holding her one day. I said, Sophia, I love you more than anything in the universe. And she turned back to me and said, Dad, universe or multiverse? Now that's how we begin, right? We have these open minds trying to understand everything in the world around us. But as we get older, right, we begin to deal with uncertainty. Like what Feynman was saying, how do you deal with a universe that you don't really understand? How do you deal with cutting-edge ideas that you don't even know if they're right or wrong because they're at the forefront and we haven't been able to test them yet? And I got a taste of how different people deal with that when I wrote The Elegant Universe back in 1999. It came out, you know, it appeared on Amazon, and as you all know, you know, Amazon is this wonderfully democratic approach where anybody can write a review of a book that they've read or haven't read. So a few days after the book appeared, you know, somebody wrote in and gave it 5 stars. I was happy, that was good. And then I read the review and they said they were so happy that someone finally had written a book on string theory that was accessible because they said it's so hard to criticize things you don't understand. And they went on to say that after reading the book, they felt string theorists a bunch of mathematical buffoons chasing their own tails, and finished by saying that the reviewer felt that the author, namely me, seemed to be about as happy as a pig in shit. And what the reviewer was trying to say is, when you don't know if ideas are right or wrong, as it is with some of these cutting ideas about string theory and other things, there can be a deep level of uncertainty. And how do you deal with it? Feynman found it invigorating. Others find it deeply uncomfortable. And that is a wonderful divide in terms of how one goes about exploring the universe. Okay, now for my story. In my final 2 minutes. I got 2 minutes left, right? Okay. So one quick story. A kind of personal story, not that personal a story, but a story about discovery. I mean, what we scientists live for are the rare moments when it all works, right? We're doing a calculation and it all comes together. And this example is one that comes from a 1990s, 1992 or so. I was at the Institute for Advanced Study at Princeton. And I was working with a couple colleagues, Dave Morrison, who's normally at Duke at that time, Paul Aspinwall, who's now at Duke as well. And we wondered whether in string theory the universe might evolve in different ways than it could in Einstein's general theory of relativity. Right? In general relativity, we all know that space can stretch, it can expand, it can twist, it can warp. But one thing that can't happen in Einstein's general relativity is space can't tear apart. Can't tear apart and, say, repair itself. That tearing process would yield to physical phenomenon that would be disastrous, and the mathematics doesn't allow it to happen. We asked whether, in string theory, space might actually rip. So we broke this problem into 2 parts. Dave Morrison and I tried to work out the mathematical calculation that would give us insight into whether or not this tearing process could happen. Paul Aspinwall was working on the computer code that was going to implement these mathematical ideas and do the final calculation to see whether it was possible. And we phrased the calculation in terms of a physical parameter. You can think of it as the mass of a particle. We asked ourselves, if space ripped, would the mass of that particle smoothly change, or would it abruptly change in a way that would establish that that process was discontinuous, couldn't happen? So Morrison and I, we spent months working out the mathematics that needed to be plugged into the computer program. Paul had finished the program, was waiting for our results. It was a Friday night in the Institute for Advanced Study. Quiet, right? It's a very quiet place at night. And we finished up, and we wanted to put it into the computer program. So Paul, who'd already gone home, he called him up and said, Paul, can you come back? You know, we finally got it. We can put it in, and we can hit the button and see whether this happens. And Paul said no. It was Friday night. He wanted to watch TV, and he wasn't going to come in. He said it can wait until Monday. So we said, Paul, will you come tomorrow morning? He said, look, the only way I'm going to come tomorrow morning is if you buy me a 6-pack of beer, and it's waiting there for me. We said, okay, it will be waiting. So he came in the next morning, put in our result into his computer program. We all huddled around the terminal, and Morrison hit the enter button. And what we were looking for, what we'd boiled it down to, is if it came out, sort of sounds like Douglas Adams, it's not, if the number 12 popped out, this is real, if the number 12 popped out of this computer calculation, it meant that space could tear in string theory. So we huddled around, he hit enter, and instead the number popped out was 3.99999. And we're like, oh, God, it didn't work. But wait, we said 3.999. It's so close to a whole number. Maybe it's just a round off. I remember it's really 4. And maybe we just lost a factor of 3 somewhere in the calculation. So we go back to the calculation. We put it up on the board. Lo and behold, we find the missing factor of 3. We put it back in, hit the enter button again, and out it comes 11.999999. That's the round off to 12, and it worked. And at that moment, I just ran around the office because we were looking at something that nobody else had seen before. We were looking at evidence that if string theory is correct, that space could tear apart and repair itself in a way that Einstein's ideas would not allow. It was this thrilling moment to look at this new phenomenon coming out of this research. And that is really what science is about. It's those moments where you're looking at reality and you're peeling away a layer that nobody else has been able to peel away before. And it's my strong feeling that we scientists, look, we have those moments rarely, a few times in a career maybe. But if kids could even have a small glimpse of that, even by solving problems that we know already have answers, but that moment of going from confusion to clarity, that transition is what science is, and that's what makes it exciting. And if only more kids would have that experience, I just think it would change the world. Thank you very much.
Now you know why I'm so proud of my boy. Ira?
Okay. Thank you. The story I'm going to tell tonight is about surprise. Science is all about surprise. Scientists love to be surprised. And when they tell you they're looking for the Higgs boson, they would rather not find it, actually, when you talk to them, because they can still hunt for it and be surprised about finding it later. It's almost disappointing for some of them to actually find it. And you discover this. I've been doing Science Friday for 22 years now. And we will continue to do it for another as many years as we can. And during those years, I've interviewed a lot of scientists, and they always, as people, will surprise you by what they say. They are people, and you think you know how they're thinking, you think you know what they're thinking, you've read all about them, you've worked with them over the years, but they will surprise you nonetheless. For example, Oliver Sacks. You know who Oliver Sacks is, the neuroscientist? Yes, he's written a lot of interesting books. And he always comes on Science Friday when he has a new book out. And so one time he was scheduled to come on Science Friday and talk about his new book. And he's such a great interview. We all like to talk to him, but we always give him an hour to talk. Say, come on for an hour, because we really isn't long enough, but that's all we have. But this time, we had a special event, and we could not put an hour for Oliver Sacks. So we called up his producer, his assistant, and we said, you know, we're very sorry. We would like to interview Oliver for an hour, but we can only do 40 minutes. Well, why not? Well, because we have an opportunity no one has ever had before. Someone is searching for a giant squid in the South Pacific. And we have an opportunity to interview the captain of the boat, the scientist on the boat, live for 20 minutes before the end of the hour. So we can only put Oliver on for 40 minutes and not the last 20. I said, I'm sorry, you know. It was a long silence, and the handler said, are you kidding? I thought we were losing Oliver forever. He said, giant squid, that's Oliver's favorite subject. I kid you not. Would you allow him to sit through that whole interview and let him stay on as you're interviewing the scientist? Let him sit there and listen, maybe? We'd be very happy to have him come on for 40 minutes. I said, wow, I never knew this about Oliver. I knew all this kind of stuff would happen. This is very surprising. So sure enough, Friday came around, and Oliver Sacks comes walking into the studio with a T-shirt with a giant squid on it. And in each hand, he has a rubber squid that he is squeezing in one hand after the other. As like a kid in a candy shop, he's going to talk about the giant squid. So I said, Oliver, sit down, and we talk about his book, and I can see that he's squirming to get on to the next interview, where he's not really that interested in his book. So sure enough, 40 minutes after the hour, we come on, and I said, Oliver, you can sit here and wait through the interview if you'd like. We're going to talk to him. He says, yeah, please, let me sit down and wait with you. So we get the captain of the boat on, and he starts talking about his search for the giant squid. And Oliver says, can I ask him a question? Go for it. And he starts talking to, I could sit back and put my feet up now. I know he's doing the interview and talking to the scientist looking for the giant squid. So surprised, so much stuff that you never expect scientists to happen. The other small surprising event I'll talk to you about is when Jane Goodall. Jane Goodall has been on our program, yes, many times. About 10 years ago, I'm going to pull that out of my head because I'm not quite sure she's been on so many times. She came on the program, and once again, we gave her like an hour to herself. And I like to get calls in. It's a talk show, and I like to get the listeners in. And I had used up so much of the hour just in a great conversation with her that I had looked at my watch. I had about 2 minutes left. I have to take one call. Let's go to one call. Guy's on the phone. He says, Dr. Goodall, it's so great to talk to you. Thank you for being on the program. Do you think there is another primate out there that we haven't discovered yet? Gee, I hadn't even thought about asking that myself. And she said, yeah, there really is one. And he said, well, do you think that you're going to actually discover it? She says, yeah, I think we're getting closer and closer. So I said, wait, time out. I'm the third person in this room, and I don't know what the both of you are talking about. Obviously, you two do. But I'm going to take a guess. Are you talking about Sasquatch? Yeti? The abominable snowman? And she said, yes, we are. That's what we're talking about. And I said, Dr. Goodall, do you think that you actually can find one? She says, well, we have fibers now, hairs that have been taken off of trees and things, and maybe we can do DNA analysis and actually figure out what this thing really is. But I really believe that it does exist. My director says in my head, time's up, you're out of time. and it turns out that she had come on in subsequent years and in years that she's always admitted that she does believe in the existence of Sasquatch. She wrote a foreword to a book that was entitled The Science of Sasquatch, which did not take any side one way or the other, but just presented the evidence. So my story tonight, and I'll conclude it, is that we are always surprised in doing science as science journalists, and it's such a pleasure to find scientists who are willing to talk and tell us why they are surprised and to share their surprises with us. Thank you very much.
Great, thank you, Ira. The next speaker never ceases to surprise me, so go ahead.
Okay. Lawrence, before I begin, I just thought I would, you said that we're all sharing molecules from the breath breathed by Feynman, but you didn't say how that can be true. And so I would like to add information to this, that it is true because for every breath you take, you inhale more molecules of air than there are breaths of air in the entire Earth's atmosphere. And it's because of this fact that anytime someone has exhaled in the past, there are enough molecules to spread into everyone's breath. And so what is true for Feynman would be true for any person throughout history, including Genghis Khan, Beethoven, Jesus, whoever is your person.
No, real people.
You're sharing.
Time's up. No, it's okay.
All right. So it was the 1700s, and William Herschel, the most famous astronomer of his day, who had the biggest telescope around, making discoveries that only the biggest of its kind would give you. Because in astrophysics and in particle physics, bigger is actually better. In all cases, essentially. Big telescopes, big particle accelerators, we're together on that one. William Herschel is very well known. He's wealthy. He's funded by the King of England, King George. By the way, that's the George of American Revolution fame, the one where John Hancock wrote large so that even King George will be able to see the signature. Herschel, kind of by accident, discovers a planet beyond Saturn, the first human being ever to make such a discovery. All planets closer to the sun than what Herschel discovered are quite visible to the unaided eye at night. So no one person is credited with any of their discoveries. Cavemen saw these planets. So he wanted to name it after his funder, which is what any good scientist would do if you want to keep the money flowing. So for a brief period there, about 5 years or 7 years or so, the solar system was Mercury, Venus, Earth, Mars, Jupiter, Saturn, and George. Okay. I have books from that slice of time that enumerates the planets, and there's George right there. So clearer heads would ultimately prevail, and the planet would be named for Roman gods, as the other planets have been named, and thus was born Uranus. However, you didn't want to piss off the British, because they were really powerful at the time, and so as sort of recompense, the moons of the planet Uranus, rather than named for Greek characters in the life of the Greek counterpart of the Roman god after whom the planet is named, so for example, Jupiter has Ganymede, one of its moons. Ganymede was the manservant of Zeus. Zeus is the corresponding god to Jupiter. In that way, the Greek and Roman heritage of this whole activity is honored. So Uranus is the lone exception in the solar system to this, and all of its planets are named after Shakespearean fictional characters. That to keep the British calm. Now, I say all this, and that's not even the story I'm going to tell you. I'm going to talk about his son, John Herschel. John Herschel, also an astronomer. Not quite as well known as William, but in my field, we all know who and what he is and what he accomplished. One of the things he did in the early 1800s was essentially invent color photography. He made major contributions to putting an image of reality onto something that captured that reality for others to share. Arguably one of the most important inventions for the recording of scientific data there ever was. That was in 1839. He called it the cyanotype. Time would move on. We would not perfect color photography for a century after that, really, but photography was born in the mid-1800s. The first war to be captured by photography was the American Civil War, the 1860s. Film was not very sensitive to light, so you had to sit for long periods of time. That's why there were no action photos from the middle of the 1800s. And in fact, if you were posed for the photo and you just like scratched your nose, you were a blur in the image. Now, why? I'm taking you down this road because in that era, for the first time, a portrait of you did not require an artist. You would hire an artist if you were wealthy to paint your picture. And you'd want it to be accurate or make you possibly look a little better. Over that period, from 1840 through the 1860s, all of a sudden, art did not have to capture reality. It was no longer the obligation of the artist because we had photographs to do that. And in that period, Impressionism was born, where the artist said, I'm not going to paint what I see, I'm going to paint what this image feels like to me. 1888, we're still in this period. Van Gogh, in the early morning hours. Van Gogh paints. I know some of you were worried I didn't have a cosmic tie on or my vest. I wasn't going to let you down. All right, so he paints this. It's called The Starry Night. And I bring up this painting for several reasons. First, we know it was painted in the pre-dawn hours because that's the only way the moon can be angled that way towards the horizon in the northern hemisphere. That makes this pre-dawn. We're pretty sure the brightest of these stars is Venus. Venus, the planets are typically what come out first in the evening, which is why most of your wishes have not come true. You've been wishing on planets. All right, so that's just how that works. But planets can also be in the early morning sky, as was this painting. By my read of paintings ever drawn, when I look at this, there's a foreground. There's a cypress tree. There's a village. There's a church steeple. But he didn't call the painting Sleepy Village, Cypress Tree, church steeple, hills. It is the first painting that I know of. I don't claim perfect knowledge, but I looked hard. It is the first painting I know of where the background is the subject of the painting. And that background is the night sky. And it is elevated the cosmos to become fair game to the artist. And I submit to you that scientific discovery, especially cosmic discovery, does not become mainstream until the artists embrace the fruits of those discoveries. So I applaud Vincent van Gogh for thinking that the sky is what mattered more than anything else in the foreground for this painting. And one point at which I will end on because my time has run out. Sorry.
I'm sorry, Neil.
Yeah. So, I forgot what I was going to say.
Start over.
So,
the sky is the subject of the painting.
Yes, thank you.
The first time in history.
Thank you, sir. Right.
The sky has entered the mainstream.
The sky is the subject of the painting.
The sky is the mainstream.
Over that time, from the 1880s into the 1900s, many discoveries were being published. Newspapers came of age in a big way so that the dissemination of cosmic discovery was shared by all. And I submit that opened up a new era of the public awareness of cosmic discovery. The popularity of Einstein in 1905, right up through 1916, that continued to rise because media took charge. And so I see that as sort of a watershed period that is continuing to this day with things such as the World Science Festival. The fact that there are radio programs that value this, that people listen to and care about. One last point. I had criticized the sky over the sinking ship of the Titanic to Jim Cameron. I was nipping at his heels for 10 years on this, and he finally actually fixed the night sky. And and called me a son of a bitch, but in a loving way. It was a loving son of a bitch. I was asked, given how nitpicky I was about the wrong sky over Kate Winslet as she floated on that plank, they said, what do I think about the Van Gogh sky? Clearly that's not accurate. My reply was, in the case of the artist, I don't want them to represent reality because I have that via my own telescopes. I want and I need the artist to take me to new places. And the new place Van Gogh took me is not the sky as it is, but the sky as he felt it. And the more of us that feel the universe, the better off we will be in this world. Thank you.
Back on. Put it back on. There you go. 12 minutes. Right. I think we have some time left. I do want to say two things. First of all, you notice Pluto is not on this curve. And secondly,
get over it.
And are you sure?
And what really, actually, the other thing that really worried me for those of us backstage in the dressing room was, well, you haven't seen the underwear, but in any case, moving from something to something else. I don't want to say it. Let me call on Richard. Thank you.
Without ever violating the laws of physics in any way whatsoever, Darwinian natural selection has put together on this planet, and I would conjecture on rather a lot of other planets as well, something utterly extraordinary. The world of complexity, which is unknown to physicists, the world of complexity, which is the world of biology, and on this planet at least has produced the human brain, which is capable of understanding the process that gave rise to it, capable of making a model of the universe in which we stand. I have coined the phrase the genetic book of the dead to describe the gene pool of a species, in the sense that the chisels of the sculptor, which is natural selection, work away at carving the shape of the gene pool of the ancestors of every animal and plant alive, carving it into the shape required for the animals concerned to survive in their particular environment. And what that means is that the gene pool of, say, a camel is a kind of description of ancestral deserts. The gene pool of an antelope is a description of the savanna of the ancestors. It's a description of the lions or leopards that the ancestors escaped from. And reciprocally, the gene pool of a lion is a coded description of the prey that the ancestral lions caught. So the gene pool of every species is a unique informational description of the ancestral worlds in which they survived. And mostly all the genes in the gene pool share the same ancestral history. They all share the same, we could almost call it, experience of the past, ancestral experience. But wouldn't it be interesting to find a place where some of the genes in the gene pool have had a different ancestral experience from others? This would be a critical, almost an experimental test. And I want to tell you a story about one such example: cuckoos. The European cuckoo parasitizes quite a large number of different species. You know they're brood parasites. You know that the female does not lay an egg in her own nest. She goes and finds a nest of a host species. It might be a hedge sparrow, it might be a meadow pipit, it might be a reed warbler, it might be a robin, and deposits an egg in the nest, having removed one egg from the host nest. The young cuckoo hatches out first, before its foster siblings, and then the first thing it does is to toss out the eggs of the other of the foster species. The young cuckoo, the first thing it does, it gets the egg into a sort of hollow in its back, and it shuffles its way backwards over the edge of the nest, tosses the egg out. Obviously, it has no idea why it does it. It's got no idea of anything very much. This is built into the nervous system. And the cuckoo has many, many other fascinating adaptations to its brood parasitic way of life. Now, here's the point. The same species, Cuculus canorus, the same species parasitizes a large number of different host species, and when it lays an egg in each of the nests, each host species, the eggs mimic those of the host species. So when a female cuckoo lays an egg in a reed warbler nest, the egg that it lays looks like reed warbler eggs. When it lays it in meadow pipit nests, the egg is dark, almost black. It looks like a meadow pipit egg, and so on. How can this happen? How can the female cuckoo possibly produce the right kind of egg, given that it's got the same genes as all the other cuckoos in the species? It's all one species. It's a bit of a mystery, and the answer is almost certainly known, and it comes back to my point about different parts of the gene pool having different experience. Each female cuckoo learns the nature of the nest in which she herself was brought up. So there are females who are brought up in robin nests, and they return when they're adults to robin nests and lay eggs in robin nests. A female that was brought up in a reed warbler nest, when she grows up, she will return to reed warbler nests. Well, that's all very well, but they're still the same species. Now, here's the thing. As you know, in mammals, sex determination is done by an XX-XY system, such that males have different sex chromosomes. One is called Y, one is called X. Females have the same X and X. And if you work it out, when you cross an XX and an XY, 50% of the offspring will be XY male, 50% will be XX female. So a Y chromosome in a mammal like us has only had experience of male bodies back through history. X chromosomes have had, 2/3 of their time in female bodies and 1/3 in, have I got that right? I can't be bothered to work it out. But the point is that in birds, it's the other way round. In birds, it's the female sex, which is XY, and the male sex, which is XX. So there is one part of the genome of a female cuckoo which has only ever had experience of female bodies, and a robin cuckoo female, her Y chromosome can look back on a long history of nothing but robin nests. Well, not quite nothing but at least for a long way, nothing but robin nests. A reed warbler female has got a Y chromosome that can look back on a long history of reed warbler nests. All the other genes in the genome can look back on a mixed history of all the different species that are parasitized. But the Y chromosome has unique experience. And so the whole thing is explained on the hypothesis that egg coloration is carried on the Y chromosome. And that enables females to be specialists in one particular kind of host. They learn which kind of host they were brought up in themselves, and so this learning process sees to it that the Y chromosome has this unique experience. Now, every now and again, a female cuckoo will, of course, make a mistake. They're not perfect. Nothing's perfect. So a reed warbler cuckoo, for example, may by mistake lay an egg in a robin nest. And of course, her egg will then be very conspicuous. It won't look right. And the chances are that it'll be killed. It'll be thrown out by the foster parent. But that's how these new genties, as they're called, female races, these new genties come into being by females making a mistake. Now, if you look at the perfection of the egg mimicry in the different genties, the different races of females, only females have races. The males are all the same race, if you see what I mean. Robin cuckoos are exceedingly poor mimics of robin eggs. Meadow pipit cuckoos are exceedingly good mimics of meadow pipit eggs. And the hypothesis of Nick Davies, who's the main person who worked on this, is that cuckoos and their hosts are engaged in what's been called an evolutionary arms race. Arms races occur between predators and prey, parasites and hosts. And the idea is that robin cuckoos have only recently entered upon their arms race with robins. And therefore, neither the cuckoos have had time to develop perfection of egg mimicry, nor have the robins had time to develop perfection of discriminating the eggs. And that's why the egg mimicry is poor, and yet it still works. Whereas meadow pipits have been engaged in a much longer arms race against meadow pipit cuckoos, and that's why both of them have reached perfection, have reached a much higher level of perfection. On the cuckoo side, the egg mimicry, and on the meadow pipit side, the discrimination. Isn't nature wonderful?
Cool. Fantastic story.
Bill, cuckoos?
Cuckoos. Sort of. Oh, great. Science! Thank you all. It's so good to see you. Unlike, I believe, all of my colleagues, I am an engineer. I mean, let me emphasize, like my colleagues, I'm a human, but engineer. And maybe some of you saw that right away. People recognize you at parties. Hey, you're an engineer. Your pants don't reach the floor. That's how you can tell. Hey, listen, man, can you fix the blender? I mean, you're the engineer. Yeah, I can fix the blender. Here's what you do. Hold the plug in the wall firmly. And then just hold the blender motor under some cold running water. Now, see, that's funny if you're scientifically literate. So my older brother, tremendous influence on me, had a wonderful physics teacher, Woodrow Wilson High School, Washington, D.C. And he told my brother the story, who told me the story. Michael Faraday, in 1828, then through 1831, would do the Christmas lectures in London, which is back east someplace. And he did this demonstration where he had a coil of wire on one end of a laboratory bench connected to another coil of wire by two wires, the terminal wires of the coils. So he goes down here with a bar magnet, reasonably powerful magnet, which you could find in those days, and moves it, if I may, in and out of the coil with respect to the coil. And then, yeah. Here's the thing, I was in college, okay? And I don't want to trouble you. I know there are a lot of grown-ups here and stuff, but that never goes away. It's still funny. The X, Y, X, it's still there. So he moves the magnet at this end of the table, and the compass needle moves at this end. As if by magic. Of course, it wasn't magic, it was science! Yes. So the story was embellished. And it was presented to me that he did this demonstration with such success so often that he presented it to the Queen of England. And the Queen of England is supposed to have said to him, Mr. Faraday, of what use is it? And here's where I just admire the guy, and I admire what we in the United States perceive as the British way of thinking. He did not say, lady! What? Would you look? That's at that end, I'm at this, I'm not touching it. What? Are you high? I mean, come on.
I love it. You guys are awesome.
But that's not what he said. According to the story, he said, Madam, of what use is a newborn babe? Now, I don't know how much time you have spent with newborn babes, but they're not that useful. They're loud, and they leak, and there's a lot of times they don't seem to understand a word you say to them. But with that said, everybody, first of all, I mean, looking with all due respect, it was King George IV at first, and then it was William IV, so there was no queen involved. When I did the Science Guy show, we had a researcher who was very diligent about this, and he never presented it to the monarch. He presented some woman, a normal person, came up to him and asked him this question. But look around, everybody. Everything in this room, everything, the lights, the curtains, the paint, the clothes you're wearing, the upholstery, the floor, the stage, everything here owes its existence to that discovery, to the discovery that not only is there a connection between electricity and magnetism, but there's a connection between electricity and the moving of the magnetism, the flux. And that discovery, dare I say it, changed the world. But this process of science that this guy spent, I guess, he took tremendous pride in his demonstrations, and he really perfected this to show it to people. This discovery had a deep effect on me. Now, when I was a kid, I delivered the newspaper. I was a paper boy. That was the title. In the Washington Post on Sundays, there'd be Ripley's Believe It or Not. It's still there. It's a different paper, but still there. And it would say from time to time, they would run the story roughly, according to aerodynamic theory, bumblebees cannot fly. And this made quite an impression on me. And I spent some time watching bumblebees. And it became clear to me that the bees are fine. The problem is with the theory. So I wonder, continually, how many things are right under our nose that we just don't know anything about. I had a Sky Streak airplane, which are still manufactured, and the older boys showed me how to lubricate the rubber motor with dishwashing soap, and I wound that thing up, man. I wound up that rubber band, and I got the thing wound up 350 turns, man. And I read on the back of the package that you can steer the aircraft by bending the vertical tail, the rudder, making a rudder, sort of. Bend. Now, okay, this is an eyewitness account, and it's from one guy. Eyewitness accounts are imperfect, and this is the way I remember it, okay? Now, most of the time when you operate these aircraft, if you've ever tried it, it's two hands. You throw it like that, or you throw it like that. But one time I threw it, and it made 3 perfect circles, and it came right back to my hand, like a boomerang with Bugs Bunny or something. And then I realized that I could influence objects. I realized that if you could understand things enough, you could make things and shape things and imagine traveling around the world. And you could do it with a balsa wood airplane. Just think what you could do if you worked for a big company like Boeing. And that's what I ended up doing. I worked on 747s. Relax, everybody. I was very well supervised. But these things that happen to you when you're a little kid influence you so much. And I'll bet you everybody in here is a science enthusiast, got excited about it before you were 10 years old. And this passion, this drive to know our place in the universe is what makes us special. It's what makes our species worthy. And with this PB&J, this passion, beauty, and joy, we can, dare I say it, change the world. Thank you. Happy engineers, you people! Thank you.
Yeah,
it's very good. You know, now that I've tried this, I don't think I could live without it.
Neil, you want to talk about our world or another one?
This one.
Okay.
So actually a parallel universe to this one called Ames, Iowa, which is the town where I grew up. It's the home of Iowa State University, which is a school that in a lot of ways is similar to this one. The main difference being that unlike ASU, ISU is not embedded in a great big city. So it's a kind of a self-contained academic community out on the high prairie. And Ames, different universities develop different sort of areas of specialization depending on who's working there and what they're good at. And one thing that Iowa State got pretty good at in the middle of the 20th century was metallurgy. And so when metallurgy became a really important topic during the Manhattan Project, some of the people in Ames were called upon to make use of their skills in refining uranium. So I'm not talking about enriching uranium, which is a more difficult process and requires bigger equipment. I'm talking about the simple process of taking the ore that is mined out of the ground and producing a fairly pure sample of uranium from that. They needed it because a few hundred miles off to the east in Chicago, in a racquetball court, the world's first atomic pile was being constructed. The way this thing was built is basically a big cubical stack consisting largely of blocks of really pure graphite. And among the graphite was uranium in a sort of roughly spherical configuration. And based on the calculations that they had done with the samples of uranium that they had a pretty good idea of how big that sphere was going to have to be in order for them to get the critical reaction that they were looking for. So they built this thing up one layer at a time using the uranium that they could get. And at some point, a new kind of uranium started coming in from my hometown, which is called Spedding's eggs. So Frank Spedding was a metallurgist who worked there. And he and some of the people he worked with had come up with a new way of refining uranium, which is based on the thermite reaction. So I don't know if you know about thermite. It's a very popular chemistry experiment among young and old pyromaniacs, but you take basically rust. I thought that would bring some people out of the woodwork. You take basically rust and aluminum and mix them together, and once you get it lit, which is difficult to do, but once it gets going, it's incredibly exothermic and it's spectacular, and you end up with molten metal all over the place. So anyway, it's a good way of getting oxygen stripped off of one metal and moving it over to another one, and that was what they needed to do in the case of refining this uranium. Of course, just making a big pile of powder out in the middle of the prairie and setting fire to it wasn't exactly the right way to go about it. And so they built these sort of crucibles, these really thick-walled crucibles in which they would mix the ingredients, and then they would weld it shut and set fire to the thing, and the reaction would take place inside. And much, much later, it would cool off to the point where they could go and open up the canister, and inside would be this beautiful little oval sort of this hardened puddle of uranium, hence the term Spedding's eggs. Not quite like cuckoo eggs, but much more powerful in a certain way. So these were then put on trucks and transported to Chicago and incorporated into the atomic pile. And these eggs were so much purer than the uranium that they had been working with up to that point that they actually had to change the design of the pile at that point. So if you look at a cross-section of that pile, as it was finally built, the bottom part of it is a perfect geometric sphere, but the top part is a kind of flattened oblate sphere, because they realized that they didn't have to have as much uranium because they were getting better stuff from my hometown. So that was the kind of place that I grew up. There were kids in my Boy Scout troop whose dads had been present in that racquetball court when the reactor went critical. There were, this is kind of a digression, but one of my favorite aspects of that experiment was that they were worried that it might go out of control, and so they had buckets full of a solution that was known to be a poison for this reaction, a very potent damper of this reaction. And so standing on top of the pile, they had graduate students holding buckets of this stuff, and their job was to dump this stuff into the pile if the needle went beyond a certain level, which it would do very, very quickly if it happened. But on no account were they to spill even a drop of it into the pile beforehand, because it would completely destroy the utility of the pile and they would have to rebuild it. So anyway, for the rest of the Manhattan Project and after the war, Ames was still a place where a lot of that kind of research went on. And I can remember going into, I think it was Spedding Hall at the university, and seeing under glass a wine bottle covered with the signatures of the people who were present when the experiment had succeeded. I don't know if it was there permanently or on loan, but it was one of these cheap Italian wine bottles that's in a little basket, and the scientists had all signed their names on the wicker surrounding the bottle. And later on, when I was in college, I worked as a research assistant in a lab there, and I can remember talking to a crusty old technician who liked to give the young guys a hard time. And he took a bar of metal about the size of a pencil out of an envelope on his desk, and he handed it to me. He said, "What do you think that is?" And I began weighing it in my hand and guessed all of the dense metals I knew of, like osmium, because I was a smart little physics major and I knew what all the heavy metals were. And when I had run down the list of all of them, he told me that I was holding a bar of uranium in my hand. So I kind of froze up for a second, and he snatched it out and stuffed it into an envelope and said, "You probably shouldn't hold that for very long." So with that as background, I'll quickly tell a story from my Boy Scout troop, just sort of going back to Bill's comments about getting a passion for science when you're young. Boy Scouts do all kinds of projects to learn about different things, and one of the projects that we were supposed to be doing was growing plants. And growing plants is a thing that happens quite a bit in Iowa, and so it didn't seem like a terribly interesting project on its own. And so some of the dads in our troop decided they were going to enliven the thing by adding a little sciencey twist. And so one of them got some corn seeds that were as close to sort of genetically identical as he could make them. They probably had all come off the same cob or something. And he took them across campus and gave them to one of the metallurgists, who went down into the hot room, buried deep below the building, and picked them up with a remote manipulator arm and put them over a thick lead glass wall and set them down next to a highly radioactive isotope for some period of time, and then plucked them back out, brought them to the safe side of the wall, and took them to our next Boy Scout meeting and handed them out to us. And our instructions were to take them home, plant them, water them, and bring our plants back in a few weeks' time. And one of us, there would be one prize given out for the tallest plant, and another prize given out for the weirdest mutation. And so we all participated in that project, and my plants died because I'm that kind of guy. I am the notorious black thumb, but we got both kinds of plants, both sort of fully normal-looking corn plants and other plants that were not identifiable as corn by anyone who's ever seen corn, and we had all seen it. So that's what it was like growing up in my town, and it's an interesting and touching thing about that place that I didn't realize how weird that was until I had left that town and gone off to places where when I would tell stories like that, people would look at me in a very funny way. So thank you.
You know, when I was a kid, I worked at a folk festival, and I love music, although I'm not very musical. And I remember specifically a few events where the best musicians in the festival would be asked to improvise. And it was amazing, because you'd see the first one, and it would just blow you away. And then you think, oh, the poor second guy. And they'd blow you away. And what you watched was this incredible buzz of talent and excitement, because each person was excited by the person before them. And you know, when I put this together, we had no plans. I just